All right, welcome to Project 2, the buoyant force. My name is Jack.
I'm Troy.
And I'm Gordon.
All right, so our topic is buoyant force. So buoyancy is the tendency to float in water, air, or some medium of fluid. Some ideas are that the buoyant force is always faced upward on any object in fluid, somewhat like normal force, based on the idea that pressure increases within depth within a fluid. The greater the depth, the stronger the force of buoyancy, somewhat like air resistance and proportionate forces. An example would be a rubber duck being pushed under the water.
The force of buoyancy as an equation is made up of the density of displaced fluid times little g, representing Earth's gravitational constant of 9.81 meters per second squared, and the volume of the displaced fluid. And together, this equals the force of buoyancy. Archimedes' principle lets us manipulate the force of buoyancy's equation from rho little g v into the weight of the fluid. We can do this because rho times the volume equals mass, and mass times little g equals weight. Looking at both equations, there's no connection to depth. This tells us that buoyancy force is essentially the same at any depth. While the pressure increases as the water column above the object grows and the object gets deeper, the pressure acts everywhere on the object, both above and below. And so this does not affect buoyancy, and thus lets us represent the force as only upwards, opposing gravity. An object would be said to be neutrally buoyant if the force of gravity on that object is equal to the buoyancy force. It would be negatively buoyant and sinks if the force of gravity on the object is greater than the buoyancy force exerted on that object. And it would be positively buoyant and floating if the force of gravity is less than the buoyancy force. We can check the units of our rho little g v formula, as rho is in kilograms per meter cubed, g is in meters per second squared, and volume is in meters cubed, which together form a Newton unit, which is correct for force. Given what we have learned about each of these variables, it makes sense that these come together for an upward force. And with Archimedes' principle, we can see that force equation can be represented as mass times little g equals F, or mass times acceleration equals force, when volume and density are combined into mass. While we haven't dealt with pressure much in this class, it is intuitive that less dense things would float on denser things. Using this, we can check the intuitiveness of our model by seeing that things with more mass than the mass of the liquid they displace sink, and with less float. With volume increases, more liquid is displaced and the force upwards increases as well. If the liquid is more dense, then when it is displaced, the force reacting to this displacement will also be larger. If g, the Earth's gravitational constant, was larger, then the force acting on all of the liquid around the object would be larger, and more force would be present in the Earth to oppose the displacement. It is new to us to combine density with volume and gravity proportional to force. Similar force concepts to those explored earlier in physics, and similar variables contributing, but this is kind of a new method and new combination that we're seeing. There's lots of similarities with things like the force of gravity or other simpler forces that we have seen and dealt with, especially in 211. Intuitively, it may be surprising that there's no correlation with depth, until it is considered that the pressure from depth is acting all around the object, both below, above, and to the sides. This is similar to a pressure, or similar to the water pressure formula without the water column height, which is the pressure equals rho times Earth's gravitational constant G times H, the height of the water column, would give us the pressure.
All right, so from what we've learned in this class up until this point, in order to model a rubber duck resting on the surface of a water, we would be able to deduce that there is a force, in fact, keeping the duck above the water. And we can model this through a free body diagram as seen on the right here. We can also understand that this force must cancel out gravity through F net equals ma, which equals 0 because the rubber duck is at rest on the surface of the water. And we could potentially model it as some sort of normal force, since that's all we've kind of seen from objects resting on surfaces up until this point. But the limitations include not being able to quantify the source that actually acts on the duck, and not really being able to create any type of relationship between how much the duck weighs versus how much the surface of the water can actually support. So when the duck would actually start to sink. But in our adaptive physics model, which includes the force of buoyancy, as you can see on the right here, with the new model, we can actually quantify the force of gravity based on the parameters of volume of water displaced, as you can see by the dotted line, acceleration of gravity, and the density of the water, as you can see by rho. We can also understand that if the duck has more mass, it will displace more volume of water, or it'll displace more volume of water, creating a greater buoyancy force.
Right, so real world applications and example problems. So some real world examples of buoyancy would be cases in which objects float or fall. Objects such as balloons will have properties in which they can be filled with certain gases that can be lighter due to the density properties, such as if a balloon were to have a denser air inside of it compared to the outside air, it would tend to fall, as opposed to the opposite, which would be less dense gas in the balloon and more dense gas outside of the balloon. And really what this means is that in a fluid concept, such as with water and liquids, there would be something where like a boat would have higher buoyancy, a higher buoyancy force that counteracts due to the displacement, so the size of the boat, onto the water, which then in turn causes the boat to reside on top of the water.
So as we talked about earlier, things float in air when their density is less than that of the air surrounding them. There are two types. They could be hot gas or less dense gas. Hot air enclosed in a space like a balloon can float in cold air if the density decreases low enough as the hotter molecules fill a larger space with less mass. Gases like helium float because they have a lower density than air that they're displacing. Helium has a density of about 0.17 kilograms per meter cubed. Gases with more dense than air sink, such as carbon dioxide. CO2 has a density of about 1.8 kilograms per meter cubed versus air's roughly 1.2 kilograms per meter cubed. The difference in our equation for hot gas lift deals with the difference between outside and inside density. For this case, the lift force would be equal to the pressure outside minus the pressure inside, quantity times little g times the volume being displaced.
Another real world example or application of this would be answering the question, why is it easier to float in salt water than it is to float in fresh water? So when a human is fully submerged in water, why are they able to float more easily in the ocean versus, say, a lake? So in order to solve this, we can actually take our known values which we found off the internet, where the density of salt water is actually 1,027 kilograms per meter cubed. Density of fresh water is 1,000 kilograms per meter cubed. The force of gravity is 9.8 meters per second squared, and the average volume of a human is about 0.075 meters cubed. So doing the calculations here using the buoyancy force equation, we can actually see that the buoyancy of salt water creates or has a force of 754 newtons or 755 newtons approximately, when the buoyancy of the freshwater force has a force of 735 newtons. So through these values, it actually can be seen that the force of buoyancy of salt water is greater than that of freshwater because the density of salt water is greater, and that explains why we're able to float better in salt water.